This is the exam two study guide review session. So before I get going into going over that study guide, I just wanted to give the basic structure of how exam two is going to be in place. So it's going to follow the same suit as exam one. I will post the exam this Friday at around noonish, give or take some time, with the standard deviation of an hour or so. But around noon or so, I will post an announcement stating, hey, the exam is live, you can take it. Just like the first exam, you will have until Sunday at 11:59, just like all of our other assignments in the class. But you'll have until Sunday to complete the exam. You will have one attempt. That one attempt will be an hour and 50 minutes. And the exam will close down on 11:59 on Sunday. As far as the questions on the exam, there'll be 50 questions, all of which will be multiple choice. They'll be pulled from my test bank of questions that I've written. So no two exams are going to be the same. But yes, I will post an announcement on Friday with this information as well. But I wanted to give you this little verbal instruction on top of that. So with all of that being said, let's get into actually getting into the study guide itself. So here's our exam two study guide. So the first thing that we're going to discuss is when to reject or retain the null hypothesis using both critical values and using p-values. So when it comes to using critical values to determine what to do with the null hypothesis, we've used this pretty much since we started doing one sample t-test. We've done this very consistently, but just as, just to kind of freshen up everything, when we calculate our test statistic, so this is our step 3, when we calculate our t statistic or our f statistic, we are comparing that value, whatever we get from step 3, to our critical value. Now, it's important to note that for most tests, they are going to be two-tailed. Our one sample Z, one sample T, independent and dependent samples t-tests are two-tailed. This means that our critical values can be positive or negative. So it's important to note that when we have a negative test statistic, let's say we do our calculations in step 3, and let's say we're doing some sort of t-test, we get a -2 for our t statistic. We would need to compare that to our negative critical value. So let's say it's -2.042. So in determining significance and deciding whether to reject or retain the null given this situation, if we want to reject the null, then our negative t statistic would need to be less than our negative critical t value. So I mentioned if we calculate -2 as our test statistic and our critical value, the negative critical, is -2.042. Well, our negative critical value, our negative critical value of -2.042 is slightly smaller than our -2 value. So this would mean that we are retaining the null hypothesis. If we were to draw a normal distribution, kind of think of it as a number line where we have our distribution with 0 in the center, and on the tails we list +2.042 and -2.042. If our value falls anywhere between those, then we would retain the null. So -2 is slightly greater than our negative critical value of -2.042. So we would retain the null. If we had a t statistic of -2.1, well, that is less than our negative critical value of -2.042. So we would reject the null. And when it comes to positive test statistics, we would compare it to its positive critical value. So same situation, if we had a +2 for our t statistic, and we're comparing it to our positive critical value of 2.042, we would also retain the null. 2 is not greater than 2.042, so we would retain it. But same can be said that if we had our t-stat at 2.1, with the same critical values, we would reject. So anything that you do for the positive test statistic, your positive t, you will also do for your negative t. So keep that in mind. The only test that does not have this positive or negative nature would be with ANOVA. Since ANOVA is an analysis of variance, that's what it stands for. We know from way back in the day that variance can only be positive. All measures of variability can only be positive. The lowest value it can be is 0. So when we're calculating our F statistic, this is the step 3 calculation for ANOVA. Well, the only thing we're going to get is a positive F value, assuming we don't get a 0. So in determining whether we reject or retain the null with ANOVA, well, that's only going to be compared to positive critical values because that's all that ANOVA can give us. Now, when it comes to p-values and deciding whether to reject the null, I like to think of it like a limbo bar. Instead of comparing our test statistic to our critical values, that's one pair of determining significance, one way that we can decide whether we can decide what we're doing with the null, pardon me. The other pair is taking our p-value and comparing it to alpha. So p-values typically come in decimals, but they are essentially probability. You can see them as a percentage as well. For example, a p-value of 0.04 would also be a 4% p-value, but I digress. So when it comes to comparing p-value and alpha and deciding what to do with the null, think of alpha, which we have pretty much set as a standard at 5% or 0.05. Think of alpha as our limbo bar. If you are good at limbo, if you are significant in limbo, you can get under the bar every time. You're not bonking into it. You're limber enough to climb under it or like walk under it, whatever. But the same goes for p-values. If you have a significant p-value, it will be under the bar of alpha. It will be less than 5%. Excuse me. 5% is our threshold. That is our guide. That is how we know what we're going to do with the null. If we're going to go below it with our p-value, we reject it. And if our p-value is above it, then we would retain it. If your p-value is equal to 0.05, if your p-value is 5%, you would also reject the null. Just keep that in mind. But pretty much, if it's under, you're going to reject. If it's over, you're going to retain. So now, moving on to the next point, what does it mean when we reject or retain the null hypothesis for inferential tests? Oh my goodness, excuse me. So I have an example here that for independent samples t-test, rejecting the null means that there's a significant difference between two groups, while retaining it means that there is no difference between these two groups. Keep in mind that for independent samples t-tests, these two groups that we're referring to are independent samples. They're independent groups. This translates to the people that are in one group are not the same as the people that are in the other. This is in contrast to dependent samples t-test, where for dependent samples t-test, rejecting the null is saying that there is a significant difference in the different scores. These two groups of the same people, when we reject the null, are not equal. There's a difference between exam scores the first time versus the last time you take a final exam in the class. This is an example from our GE assignment. This is the dependent samples prompt. But retaining the null for a dependent samples t-test is saying that there is no significant difference between these within groups, these two samples that actually consist of the same people just being tested twice. Now, for rejecting and retaining the null for one sample test, both Z and T, it's actually very similar. Actually, the null and alternative hypotheses for one sample Z tests and one sample T tests are identical. So when we reject or retain the null, the same conclusions can be met. So for both one sample Z and T tests, rejecting the null is saying that the population provided, which is, the mean and the mean of the population. And if we have a z-test, we also have the standard deviation of the population. That population that's been provided is, when we reject the null, not equal to the population that the sample that's being provided to is. So we have a sample of 100 vegans, and we want to compare it to see if vegans as a whole population, all vegans, mention their diet at the same rate as people with non-specific diets. So if we were to reject the null in that instance, we are saying that the populations, the general, I don't have a specific diet population, and then the population of vegans, rejecting the null is saying, oh, they're not equal. These two groups, these two populations of individuals do not mention their diet at the same rate. If we retain the null, then the opposite is, then we're saying the opposite, that these two groups of individuals do mention their diet at about the same rate, the same number of times as the other. With ANOVA, when we're rejecting the null, all we're saying is that these, remember, ANOVA is where we have 3 or more groups, very similar to an independent or dependent samples t-test. The big difference is we're just adding on another group. We know with independent samples t-test, we're comparing 2 groups. You either get a study guide or you don't. With dependent samples t-test, we're comparing the same group of individuals, but we're testing them twice. So we have technically we have 2 samples here. It's just a within subjects design sample. But in this case, for dependent samples t-test, we're also testing them twice. So we have 2 groups again. The first time you take the final exam in the beginning of the semester, and then the last time you take the final exam at the end of the semester. Every person is going to take it twice, and we're comparing each person's first time to their last time they take it. ANOVA is, again, just adding on another group. So instead of only looking at people who took the final exam on the first day and the last day, maybe for ANOVA, you also take it in the middle of the semester as well. So now you have 3 scores that you're comparing for each person, not just 2. That's key for ANOVA. We have an additional group being added on here. But when it comes to rejecting the null, since we have 3 or more groups, but since we don't have just 2 groups, we can see which one is bigger, and it's really easy to see, which one's higher. With ANOVA, we don't quite have that same, we don't have that same concrete, this one is the biggest one, this is the odd man out. So when we reject the null, all we're saying is the groups are different. Oh, which one scored the highest? I don't know. For me to know that, I would have to conduct a post hoc test. Post hoc tests are only necessary for ANOVA when we reject the null. Considering that rejecting the null is saying the groups are different, and post hoc test is kind of telling us which one is the odd group out, which one is way higher or way lower than the others, we only conduct it when we reject the null. We would not conduct a post hoc test when we retain the null. Retaining the null for ANOVA is saying that all 3 groups are the same. There is no difference. So we would not need to conduct a test to determine which one is different post hoc when we have already determined, using our 4-step hypothesis testing process, that all the groups are the same. That's retaining the null. We only do post hoc when we reject. Okay. So next is when to use inferential tests provided, given information provided in the question. So there's going to be several examples, like you'll see, similar to activity 7. That was an activity we had a couple weeks ago where it was a multiple choice questions where you're given a prompt, like you're being written. Oh my goodness, I cannot talk today. Where a study is being described, and it's up to you all, based on the information provided, to pick which test would be used to analyze the difference. I will say that as far as activity 7 is concerned, I kind of had a little fun with it. Those questions, those descriptions were a lot longer. The exam will be a little more to the point. You're not going to have as many snarky comments. You'll still have a little bit of snark because I still like to write my essay questions, my exam questions with some snark, but ultimately, the questions on the exam will be similar to the ones on activity 7, just a little more to the point, more condensed. So I also want you to know the steps of hypothesis testing. So know which one comes first and what you got to do, which one comes second and what you got to do third and then fourth. So we know that the first step is to state the null hypothesis, state the hypotheses. This includes the null and alternative. I've already mentioned this, but for one sample T and Z tests, we know that those null and alternative hypotheses are identical for these two tests. The null is always going to be equal to the population mean, and the alternative hypothesis, so long as we have a two-tailed test, is always not going, it's going to be the population mean is not equal to whatever the provided population mean was. An actual number will be used here. For independent samples t-test, it's actually a little more straightforward. They're all, no matter which independent samples t-test you're doing, it's always going to be the same. It's mu1 equals mu2 for null, and mu1 does not equal mu2 for the alternative. Dependent samples t-test, the mean of the difference scores equals 0 for the null. This is saying they're all the same. And then the alternative hypothesis is that it is not equal to 0. They will not be the same. And then ANOVA, we have the null of all the groups are equal, mean 1 equals mean 2 equals mean 3. And then the alternative is saying, no, mean 1 might not equal mean 2, does not equal mean 3. So they're not all the same. Setting the criteria is step 2. This is where we are going to have our critical values come into play. So be sure you know how to read a t-table. We've used the t-table most consistently, knowing how to find your critical values. Know how to read it, but keep in mind if you do have a question where you'll be determining, where you'll be needing to use a table of some sort, there will be an excerpt of the table provided. So know how to read it, and then in the exam question that you might have, you will be provided a little portion of the table, and then you'll need to do your calculations. Let's say we're doing a Z test. You'll need to do your calculations to determine, okay, which one would I need to use if I am going to be checking for p-values. We know that our Z table has our p-values. Don't forget to multiply that value by 2 because we're always doing two-tail tests. But just knowing how to read Z tables and T tables. So T tables give us critical values, Z tables give us p-values. And keep in mind that those two are different ways to determine significance. When we get our value from the Z table, we would compare that p-value, that is what the Z table gives us, to alpha. And when we get our critical value from the T table, that would be compared to whatever we calculate in step 3, our test statistic. So keep in mind that step 3, as far as the statistics, the hypothesis testing is concerned, they all follow the same basic outline. State the hypothesis, set the criteria, calculate the test statistic, make a decision regarding the null. Step 3, of course, that's the main structure. That's the backbone of it. But the meat and potatoes on that backbone, you don't put potatoes on a backbone. That's weird. But the meat of it is going to be different depending on what test. So one sample T and Z tests, very similar. The only difference between these two is some of the wording and just how we label it. So for example, when we're doing our standard error for Z tests, that is known as an estimated standard error for one sample T, but we are still calculating it the same way, taking our standard deviation and divide it by the square root of the sample size. So just kind of keep in mind the differences in steps, particularly think of how independent samples t-tests, if you have the same sample size, if both of your between subjects groups, meaning between subjects as just referring to the fact that our two samples consist of different people, keep in mind that if we have equal sample sizes, we would use one particular equation when calculating the pooled sample variance. That's the first step in our step 3, calculate test statistic. Compared to if we had unequal sample sizes, we would use a different formula. So don't forget that. Calculating Cohen's d for these different tests. make sure you know how to do that. With one sample Z and T, it's pretty straightforward. You just take population mean minus sample mean divided by whichever standard deviation that you have. If it's a one sample Z, you'll divide it by the population standard deviation. If it's one sample T, you'll divide it by the sample standard deviation. So just review the formulas for calculating Cohen's d. I also mentioned that you, as far as calculations are concerned, when it comes to independent samples t-test or dependent, I won't have you do that for the exam. It'll be more so interpreting it. So I might say, oh, an independent samples t-test was calculated and you had a critical value of 2 and your t statistic was -1. Are you going to reject or retain the null? Well, all right, you make that decision. And then, okay, well, now that you've made that decision, what are you going to do? What does that mean for the groups? Does it mean they're equal? Does it mean they're not equal? So for independent and dependent samples t-tests, I will provide you the information as far, you won't need to calculate it, but you will still need to determine what it means. You will still need to make a decision regarding the null, and you'll also need to state, you know, what that means for your groups. So calculating one sample Z and T test, though, I will have you be doing that. So just go over that. Again, luckily, those formulas are pretty darn similar. So if you know how to do one, you know how to do the other. Just keep in mind that T tests include degrees of freedom when you're looking, when you have a T test. So that is a difference between those two. And that is solely because T tests of all variations of T tests, they deal solely in samples. So they're going to have more information regarding samples. And with more information on a sample in comparison to a population, we know there's a margin of error there. We know there is information that we're missing. That's part of what makes a sample a sample. We don't have all of the population here. Otherwise, we'd call it a population. So when we have that missing data, we tend to kind of statistically, we kind of tend to make up for it and include some margin of error. In the case of t-tests, that is known as degrees of freedom. If you think about when we calculated sample versus population variance, that was there too. It was that n-1 when we calculated sample variance. Again, it provided us a greater level of variability. The value was greater, and that was to accommodate for the missing information, casting a wider net over all the population we can't see. Next, you'll be interpreting the strength of Cohen's d. So I can provide you a Cohen's d value, and I'll ask you, what is the strength of it? Is it large, medium, or small? Keep in mind that the direction of Cohen's d, this is referring to if it's a positive or negative number, does not have an impact on strength. So a 1.5 Cohen's d would have the same strength as a negative 1.5. A -2 Cohen's d has the same strength as a positive Cohen's d. I see a lot of students kind of get caught up on the negative and think, oh, well, it's less than 0.2, so it's going to be a small or weak effect size. That's incorrect. Whatever is true for its positive counterpart is also going to be true for the negative. So again, if you have a Cohen's d of -0.6, that would be medium. If you have a Cohen's d of just positive 0.6, that is also medium. So anything that's true for the positive as far as strength is concerned is also true for the negative if it's the same number. Because it's the number that matters when it comes to interpreting the strength, not if it's positive or negative. Lastly, describing what it means for your groups or variables when you reject or retain the null hypothesis, in particular for independent and dependent samples t-tests. So I think for this one, yes, we've talked about how you'll need to know when to reject or retain the null based on critical values or alpha and p-values. But you'll also need to know when to do the tests. So again, this is going to be this point here, which test would be used to calculate this. But then describing what it means when you do reject or retain the null. What does that tell you about the groups that are provided? So I'll use our GE assignment prompts as an example. So for our independent samples t-test prompt, we had two groups. We had about 20 students who were provided a study guide to use for preparation for the first exam. And then we have 20 students who were not provided a study guide to prep for their first exam. Those are our two groups, students with a study guide, students without a study guide. Okay, so if we were to reject the null, what does that mean for these two groups? Oh, well, it means that the test scores, that is what we're comparing between these two. We want to see, hey, which group did better on the exam? You know, do study guides help actually increase test scores? Well, it would make sense that we're comparing the test scores between these two groups. So if we were to reject the null here, we would be saying, oh, yes, it turns out there is a difference in exam scores between students who were provided with a study guide and those who were not. So describing what it means for your groups or your variables is really similar to knowing what it means. Oh, well, you know, rejecting the null says there's a significant difference between the groups. Retaining the null is saying there's no difference between the groups. But this last bullet point is really taking it a step further and being able to kind of fill in the blanks with, okay, well, who are the groups? Oh, it's the with and without study guide students. And rejecting the null says that, you know, students, let's say, with a study guide perform better on the exam than the students without. And then retaining the null would be saying that the test scores between these two groups are going to be pretty much equal. The study guide did not make an impact on test scores. They scored about the same. For dependent samples t-test, again, let's take the example from our GE assignment. So students were provided, well, excuse me, no, that's the independent samples. Students took their final exam for a statistics course the first day of the semester, so, you know, in August or January. And then they also took that same exam again the last day of the semester, so May or December, whatever semester they're taking the class, who knows? But when we reject, so we're trying to see, all right, so as far as these students are concerned, did taking the class have them perform better on the final? So keep in mind that before they took Psych 42, or whatever the statistics class will be labeled, it could change in the future, God knows. But the first time they take the exam prior to taking Psych 42, they probably don't do so well. Maybe they took it before, so they might do okay. But generally, I'm sure a majority of students who took the Psych 42 final in January or in August didn't do so well. But then they take the class, the few months that follow, you know, they're learning all types of things. They're laughing. They're just enjoying statistics. Probably not, but, you know, they're learning at least. As the semester goes on, they get to their final in May or in December, and it's the same final that they took on day one. Well, we're thinking, hey, I think they're going to do better the second time around. You know, they've taken the class now. They know the material. The words hopefully make a little more sense. Imagine if you've never taken a stats class before, imagine taking an exam that says, oh, given a test statistic of 2.5 and a critical value of 2, would you reject or retain the null? If you've never taken stats before, you're like, what the hell is going on here? But now think, you know the answer to that now. You know, oh, if my test statistic is 2.5 and the critical value is 2, I'd reject the null. So that's proof in and of itself that taking the class could potentially have you perform better the second time around that you take that final. Well, nifty. If we reject the null for this particular dependent samples t-test, that's saying, yes, there is a difference in test scores between the first and the last time students took the final. And if we retain the null, we're saying that the opposite is true. Oh, well, there is not a difference in test scores between the first and last time students took the final. So there we go. Just filling in the blanks for what your groups are for independent and dependent samples t-tests, and knowing that knowing what rejecting or retaining the null means for those. So that's really the focus there. I gave examples, of course, but we'll have different examples on the exam. And that is our study guide. So I'm going to post this bad boy onto YouTube now. I'll post it as soon as it's done uploading and doing all its YouTube jazz. But like I said, I will post the exam this Friday, later this week. You will have until Sunday to take the exam. I'll publish the exam on Friday so you all can see it. I'll also post an announcement saying, hey, the exam is live, you can take it. You will have one attempt at 1 hour and 50 minutes. And it will be 50 questions, all of which are multiple choice. And oh, it's open note, but I'll put that in the announcement as well. I forgot to say that at the beginning of this video. But anyway, I wish you all the best of luck on the exam. Keep in mind, stop by my office hours if you have any questions. And yeah, good luck.